We've talked about introduction to mass spectrometry and we've done ion sources. Let's move on to mass analyzers and related topics. We need to talk about resolution, ion optics and detectors, and then specific types of mass analyzers. There are a lot of different ones, but we're going to focus on the ones you'll see most of the time in forensics, and that would be the quadrupole mass analyzer, the ion trap, the time of flight, the Orbitrap, and then we're going to finish up with a discussion of what's called MSMS, and the mass analyzers that are capable of doing MSMS fragmentation. It turns out this is too much for one video, so we're going to break this into two parts. And in this video, we're going to talk about resolution, ion optics and detectors, the quadrupole mass filter, and the ion trap. So when we talked about ion sources, we said that the main way to group or distinguish ion sources was how hard or soft are they? Kind of another way of asking, what kinds of ions do they make? Well, the most important characteristic in grouping mass analyzers is resolution or resolving power. There are other characteristics or features that distinguish them, but the biggest one is resolution, resolving power. So we're going to talk about the quadrupole mass filter, which just does unit mass or nominal mass. In other words, it gives you a mass, but with no decimal places, just an integer. So you can say something is 300 or 301, but you're not going to call something 300.124. Now, it's cheap and it is simple. It's hard to explain and hard to understand, but when it comes to actual implementation, engineering, and maintenance, they are cheap and simple, but they are pretty difficult to teach and to learn the concepts. The ion trap is going to have a lot in common with the quadrupole. It is also mostly going to be unit mass resolving power. You'll see that asterisk there. There are special modes that you can operate the quadrupole and the ion trap in, the quadrupole mass filter and the ion trap. That will allow you to go up to higher resolving powers, but those aren't typically used. It's a little bit more expensive than the quadrupole most of the time, but it has some extra features to it. It can do something called MSMS fragmentation, which is a really powerful feature. The main feature it's going to be used for in forensic science is the fact that it tolerates higher pressures. You can use it at higher pressures. You don't need as much of a vacuum system, and that means you need smaller electronics, less bulky stuff, and that means you can build instruments that you can take out into the field and use in the field. The time of flight, or the TOF, is going to have good resolving power. You're going to start to get accurate mass measurements here. It's relatively expensive. It's really fast, and it has a huge mass range. You can go up to mass 20,000 or 100,000. The Orbitrap has amazing resolving power, but is also relatively expensive. As I said before, there are some other mass analyzers that are useful and important in other applications, but you don't see really in use in forensic science. The magnetic sector or sector instruments are pretty important in some geology and isotope ratio experiments. The FTICR is an extremely high resolution mass analyzer, and it certainly has its applications. And there are other mass analyzers, but they don't really crop up in forensics. So we're going to stay focused on the ones that you're going to tend to see in forensic applications. So resolution in mass spectrometry, the calculation is going to be very simple. We're just going to say it's going to be the mass, so it's the x-coordinate of the peak, over the delta m. And we're typically going to define the delta m as the full width half max, or the width halfway up the peak. Now, resolution is not the same definition as it was in chromatography, where it was always a relationship between two peaks. We don't need two peaks. We don't need two peaks to do this. And we're not just going to say, okay, resolution 1.5, we've achieved resolution, we'll quit there. A lot of times you want as much resolution as you can get because it's going to give you exact mass measurements. Okay, but it's a relatively straightforward calculation. Now, if you also have peaks that are really close together in mass, they're well beyond nominal mass, so you're trying to differentiate 304.16 from 304.18, you do need resolution beyond unit mass, and you can approximate how much resolution that you need by just taking the difference between those peaks instead of the delta m. and just taking the average mass over the difference between those peaks. And that'll give you a reasonable estimate of the resolution that you need to separate those two peaks. Let's take a look at some actual data and some simulated data as examples. Let's look at an example here. So we'll do the old standard cocaine. Cocaine has a formula of C17H21NO4. Let's suppose that we are looking at the protonated molecule. We'll go over to Qual Browser and simulate that. So C17H21NO4. But because it's the protonated molecule, I'm going to add one more hydrogen on there. So we have C17H22NO4. So this is a spectrum. This is a spectrum with Gaussian peaks simulated with 1,000 resolving power. This is basically unit mass. So this is what we might expect to see from a quadrupole or from an ion trap under typical conditions. Cocaine with the protonated molecule. Ask yourself, where do these peaks come from? Okay. All right, now it's a little bit silly to show decimal places here because we can't distinguish between it said 304.15. Well, that's great, but we can't distinguish between 304.15, 304.16, etc., etc. We're really just going for unit mass. We can distinguish between 304, 305, and 306. Now let's suppose we have a mixture with pipamidic acid. This guy right here, it's some kind of antiquated antibacterial. It has a formula of C14H17N5O3. So let's suppose we also have that guy in the mix. So we're going to say, okay, there's some cocaine in there, and there's some of this pipamidic acid. I'm going to add one more H to indicate the proton. I am not going to show separate traces right now. Okay, no change there. No change there. Now, pipamidic acid. All right, and I am going to add decimals here because we're going to jack up the resolution in just a minute to where that's important. So pipamidic acid, if we look at this, they have different masses. Cocaine's 303.353. That's not an exact mass. Which we'll talk about in a minute. 303.322. They have different formulas. So they have different masses, but they have the same what we call nominal mass. They have the same nominal mass. They round to the same integer. They have the same nominal mass, but they do not have the same chemical formula. They are not isomers, but they have the same nominal mass. These are not isomers. The relationship between these two things is isobars. They're called isobars. All right, so we do not have the resolution to see these, to get these peaks. Let's try something like a TOF. Let's suppose we got a TOF and it's running at 14,000. Let's see what we get when we get up to 14,000. Okay, we still can't distinguish between the peaks. Let's go up to 25,000 resolving power. Look at that, there we go. We're starting to see two different peaks here. One at 304.14007, one at, we can't see, it hasn't labeled this guy. Okay, so let's see let's keep going. Let's go to resolving power 50,000. If we had an instrument that was running at resolving power 50, oh, I accidentally did 5,000. 50,000, resolving power 50,000. Okay, we're getting there. We're getting there. Look at that. Look at that. Now we have this separation between these two peaks. And if I broaden, there we go. So we can clearly see we were at 304.14042 and 304.15434. Okay, now these, we can see the two peaks, but also these decimal places mean something. Before, we couldn't tell the difference between 304.14 and 304.15. When we were at resolving power 1,000, if we jump back down there, it didn't matter. We might as well have the nominal mass. Just this big lump at 304. But when we get up to resolving power 50,000, all right, when we get up to resolving power 50,000, it does make a difference. We can clearly see two different peaks at 304.14 and 304.15. Now if we keep going up to Orbitrap resolving powers, let's say 100,000, we're going to have very clear distinction between the peaks. And if we go up to 200,000, then the peaks get narrower and narrower. And we can, oh goodness. So at about 50,000, we started to see the difference between these two peaks. There we go. And we can see we've got peaks here. There we go. Okay, it gets a little bit messy. Okay, so we had these isobars that were pretty close to each other in mass, but as we increased the resolution, we were actually able to distinguish the isobars. So in this case, if we had a mixture of cocaine and that antibacterial, that quinolone compound, we could see them as two separate peaks. So high resolution gets you that. It also makes the decimal places meaningful. So it can give you what's called exact mass. Exact mass. All right. Now, if we were to say, though, what if we had a mixture of cocaine and scopolamine, or as the Brits call it, hyoscine? Well, scopolamine is C17H21NO4, the structure. Cocaine is C17H21NO4. So it's the same chemical formula as what we have in here. So it's going to give us this 304.1402. It doesn't, 0.14042. It does not matter. We can have all the resolution in the world. We can go up to resolving power 1,000,000. And it does not matter if we have isomers. They have the same exact mass. So you can't use exact mass to distinguish isomers. But it is very powerful. Exact mass is very powerful for distinguishing isobars. And then more to the point, let's look at an example of how once you have a really good exact mass, once you have 4 decimal places reliably, preferably 5, then you can determine the chemical formula from that exact mass. So this is actual data from an Orbitrap. So there's a lot of peaks in here, but they're all real. It has such high resolution that it can distinguish these peaks. So you end up with these spectra that you can really zoom in on a lot. So if you zoom in here, it looks like, oh, there's a bunch of noise and stuff, but they are real peaks. You can keep zooming and zooming and zooming, and you can see it can clearly distinguish these two peaks. 475.26526 from 475.18862 from 475.23089 from the. So you get tons and tons of information from these. If you have complicated mixtures, your separations don't need to be as good, and you can get tons and tons of peaks, and you can get information from all those peaks. Okay, but we reliably have now our mass out to many decimal places. So what we can do is you can actually just, in the software, you can tell it, generate formula from mass. And over here, it will in fact take that and it will run through, I confined it to CHNO. I said, okay, using CHNO, calculate reasonable formulas. So it will calculate and it will basically spit out this guy, 475.26526, is very likely C22H3909N2. This delta mm means that is the deviation in millimass units, so 0.253. So millimass units is out here. So it is, this calculation is 0.253 high from this. That is called the mass accuracy. You calculate this just like you've calculated accuracy in other classes. And we can look at an example for that. So for this mass, 475.26526, we have a mass assignment that has an absolute error of 0.253 millimass units, or 0.00253 mass units. So we could calculate the mass error for that guy, but you can just sort of cruise through the spectrum here, picking out peaks and saying, hey, tell me what this is. So this guy is C15, H39, O12, and 10 with a error of negative 0.083 millimass units. So that is, this formula lines up with 551.27426, but it's off by 0.00083 mass units. Now, you kind of have to go through and see if you can draw a reasonable structure. That's a lot of oxygen and nitrogen, but these are actually amino acids. So, I mean, this is, potentially feasible, but you have to go through and draw a reasonable structure and see what you can fit to it. But this is how exact mass can give us really powerful information, because if you have enough decimal places, you have to have good resolution. And then you have to, that's going to come from the mass analyzer. You have to have good mass accuracy. That comes from a careful calibration. And usually what they're going to do when they want good mass accuracy is they're actually going to have a lot of instruments now have two electrospray sources essentially, or they have two nebulizers for the electrospray source, two things that make aerosols. One sprays the sample and the other one sprays an internal calibrant. And so every time you run a spectrum, you have a peak in there that you know exactly what its mass is, and that helps you calibrate your mass to get good mass accuracy. But you have to have the resolution, you have to have good mass calibration, and then you can get exact mass measurements, which will give you the chemical formula. A quick note here about exact mass and calculating exact mass. You have to be careful here, because when you're trying to calculate exact mass, so say you have C4H10, butane, and you want to calculate its exact mass, you need to specify which isotope you're using, and carbon-12 does in fact have an exact mass of 12.00000, because that's how we define mass in the periodic table. But that is the only isotope on the entire, of all the elements and isotopes in the table, that has exactly what it's supposed to, 0.000. Everybody else is going to have mass defect. So hydrogen 1, its mass, its exact mass, is not 1.00000. Nitrogen 14, its mass is not 14.00000. So you need to find a table with isotopes and their exact masses and use those masses if you are going to calculate an exact mass for a compound from its chemical formula. We've seen why resolution is important, and we've looked at exact mass. Let's move on to talking about ion optics and detectors. The rough block diagram that I showed you in the previous video is a little bit disingenuous. We said, okay, we're going to have an ion source, a mass analyzer, and a detector. This can be under vacuum, which is going to be the case for the EI source and the CI source and some other sources. We said the ion source can be outside of the vacuum under atmospheric pressure, but the mass analyzer and the detector have to be under vacuum. And typically the mass analyzer and detector are going to be at 10 to the minus 5th, sometimes down to 10 to the minus 7th torr. And we said, oh, electrospray, APCI, DESI, DART, and paper spray can all be out at atmosphere. Actually, ICP is at atmosphere as well. But this is a little bit disingenuous because it turns out if you just have an ion source butted right up to a mass analyzer, you get barely any ions, or not barely any, but you lose a lot of ions. They get ionized and they just fly every which way, and they don't go into the mass analyzer. So if we look again at this guy, we said, okay, there's the ion source. That's actually an EI source. And it flies out of the EI source, and then we have a mass analyzer here. We'll see this guy later. It's called triple quadrupole. And then every ion that passes through the mass analyzer hits the detector. But very importantly, there was something there between the ion source and the mass analyzer. It's that funky guy there. It's called an octopole, and it's 8 small little poles. So that's an ion optic. So between the ion source and the mass analyzer, we have to have ion optics. And their function is going to be to focus the ion beam and also to help us go from atmosphere or higher pressures down to the low pressures required in the mass spectrometer. Because remember that when we have all these collisions, that's really problematic, and our ions can undergo reactions we don't want them to do, so we got to suck everything out of there. But the reality is, it's tough to go from 760 torr to 10 to the minus 5th torr. So the ion optics can help us reach intermediate pressures. So we said, okay, at ambient, we're at 7060 torr, and I pointed to these intermediate vacuum regions. Before we actually get into the mass analyzer, we're at 1, and then we're at 10 to the minus 3. This is in the ion optics. This is in the ion optic region. So as the pump is pumping, it's sucking in, and it gradually reaches 1 part way to the mass analyzer, and then 10 to the minus 3 part way to the mass analyzer to get you at 10 to the minus 5th. And we can see this here in this diagram of this quadrupole. This is an electrospray source for a quadrupole mass filter. And they're just showing us the electrospray source, but then they show us 2 different regions before the mass analyzer. These are 2 different kinds of ion optics. We have an entrance region here where we're going from atmosphere at 760 torr, and then where it says the empath vacuum region. That empath is going to help us get rid of neutrals and maintain ions. It's at 1 torr. It's being pumped at. It's at 1 torr. And then the next ion optic beyond that is called an RF DC pre-filter. That's going to help focus the ions, but also it's another step in getting us down to that low vacuum that we need to get to. Because it's not trivial to go from 760 torr to 10 to the minus 5th torr. This is sort of like trying to go from a fire hose to a trickle. It's a lot easier if you sort of have intermediate steps to cut down on that rush of gases flowing in from ambient atmosphere. And you sort of gradually cut it down until you get down to the 10 to the minus 5th or 10 to the minus 7, where you don't have much air or atmosphere left at all. Let's revisit some of the stuff we looked at in the last video, but with a special eye for ion optics. So we said, here we go, here's an EI source, and we're going to have the neutral coming in from the side, and it's going to go into the electron beam, and we did say, oh, the repeller. See, look at that, the repeller here is going to push that charged ion into the ion optics. So we're going to use these electrical fields to focus this ion beam. It's going to push it into the ion optics. If we look at the electrospray source, this is another diagram of an electrospray source. We saw that mechanism where you nebulize it into aerosols, into a fine spray, and it's a charged aerosol and it dries up. But the fact that that capillary, the electrospray capillary, is held at positive 3,000 to 5,000 volts, that's a huge amount of positive charge. So as they're propelled from the source because they were sprayed, but also they're charged, and as they become positively charged ions, they are repelled from that very high positive electrical field at the capillary, at the tip of the electrospray source. The positive ions are propelled into the ion optics, and then into the mass analyzer. The negative ions are pulled back to the capillary. It should be noted that both with EI, ESI, and all these sources, you can switch from negative mode to positive mode if you just switch the voltages. So if you wanted to see the negative ions here in the ESI, you could just switch the voltage on the electrospray source to -3, -5,000 volts, and then the negative ions would be propelled into the instrument, and the positive ions would be attracted away from the instrument toward the capillary. So we see that both the EI and the ESI, and actually if you look at all those other sources, are going to have some way to push ions into the instrument. And it turns out they're not pushing it directly into the mass analyzer. They are in fact pushing them into ion optics that are ahead of the mass analyzer. They're going to act as an intermediate pumping region to decrease the vacuum and also guide the ions into a nice beam so we don't lose a bunch of them. So we looked at this guy last week. This is the mass spectrometer on our GCMS. It's got the EI source right there. This is an actual picture. Let's take a closer look via a schematic from the manual. So you can see that up there. Up top we have this schematic of the entire instrument. There's the EI source, the turbo pump on the bottom. We've got some gauges to tell us the pressure. But on the bottom of this picture, we'll zoom in there, and that'll show us the path of the ions from creation in the ion source to destruction in the detector. So let's take a look at that region. We saw how ions created in the ion source are repelled out of the source with the repeller. If we're looking for positive ions, the repeller is going to be a positive voltage to repel the positive ions out of the source and attract any negative ions that formed, as well as the electrons, excess electrons. The ions are then going to be pushed into, you see they've got it labeled as outer source. And look closely, they have lens 1 and lens 2. We are not in the mass analyzer yet. Those lenses are electrostatic lenses. They're not lenses like glasses. Glasses or optics that we're used to form light beams, focus light. We're not trying to focus light, we're trying to focus ion. Because we're still trying to focus things, we call them optics. But they're typically just metal plates that we apply voltages to. So a nice simple lens that will pull the ions through and form them into a beam instead of a big messy chaotic ball is just kind of a plate with a hole in it that has a voltage applied to it. So this has these two lenses that you can apply voltages to. Then you'll see the next step in the beam. So we hope the ions are formed in the ion source, fly, and are focused by lens 1, focused more by lens 2, and then they go into what is called the pre-quad. That's the pre-quadrupole. That is a quadrupole ion guide. And then they go into the actual mass analyzer, the analytical quads. And then they fly into that conversion diode phosphor plate. That's the detector. The conversion diode phosphor plate photomultiplier tube. That's the detector. So here we have two lenses and a quadrupole ion guide. We actually don't need as much ion optics for this instrument, partly because it's under vacuum. The EI source is already under vacuum, and that helps us out a little bit. And looking at the software, we can see lens 1 and lens 2, those voltages there, 8 and 90, that's as part of the software. This is part of what's called a tune process. Now, most instruments will tune this for you. It's called an auto-tune. But it's really important that you adjust the voltages on the lenses and the ion optics to make sure you get as many ions as possible passing through. It's part of a tube. So let's look at some simulations from this really nice Mass Spec Pro YouTube page. This guy has some really good simulations. This is much fancier than that lens 1 and lens 2 we were looking at, but it's the same idea. This is called the stacked ring ion guide. Again, lens 1 and lens 2 is just going to be two metal plates there. This is a series of these metal plates, and you can apply different voltages to them. But we're going to look at a simulation now that will show what happens if you just let the ions fly through and you don't apply any voltage. You don't apply any electrical field to control the ions. And we're going to lose a lot of ions. So you can see a bunch of them just sort of hit the walls. They never make it through that other hole. They're never going to get to the mass analyzer. They're never going to get to the detector and be detected. So we lose a lot of signal here for no good reason. A nice ion optic will do this. You turn on this electric field and it focuses those ions. It keeps them on task. It gets them through that second hole and it pushes them nicely into the mass analyzer so that all those ions we worked hard to form in the ion source actually make it in the mass analyzer to be detected. So this guy has this EI source. The ion optic here is actually it's an ion guide called an octopole ion guide. So let's take a look at that specific ion guide right here. So if we sort of zoom in on this gap here, that is the gap between the ion source and the first ion optic, an octopole ion guide. And you can see it's a series of rods. It's 8 rods, 8 poles, hence the term octopole. So the ions fly out of the ion source through that bit of open space and into that octopole. Now here's an octopole that I've taken out of an instrument, and we'll sort of take a look around. And what your vision is a series of 8 rods held in a very careful geometry. But look, it's an open tube on the inside. It's an open space for the ions to fly through. It's kind of a tunnel that can either focus, or every once in a while we want to defocus and get rid of ions. But for the most part, we want to help the ions that are formed as kind of a cloud in the source fly through this tube and get to the end. This is a quadrupole ion guide. It's a picture, and if you look on the end of it, you can see it has 4 poles, and they're square. That's okay, but it's also just like the octopole we looked at. It essentially forms a tube in the middle, and the ions can be focused and fly through that tube to give us a nice ion beam and capture as many of those ions as possible and keep them all lined up in a nice shaped beam for the mass analyzer to do its job as best as we can. So most of these ion guides are going to be octopoles, sometimes hexapoles, or quadrupoles. They're going to be a series of poles that form a sort of tunnel in the middle. We're going to revisit the idea of the quadrupole later, because it turns out you can also use quadrupoles as mass analyzers, not just as ion optics. But let's take a look at a simulation that the Mass Spec Pro did of using a multipole as an ion guide. All right, so this is a cutaway, and you can see when there's no electric field, there's several different ions. There's green, red, and black, and they just sort of fly all over the place. They're not focused. Okay, they come in that hole. Now, if we use a proper electric field, if we use the proper voltages, wow, look at how focused the black, the red, and the green ions are there. So they come in that entrance hole, they're nice and focused, and they leave in a focused tight beam going into the mass analyzer. So if we take a look again at that zoom in, now we have a better idea of what we're looking at. We have the source, the EI source on the outside that has a repeller. It pushes the ions. If we're in positive mode, the positively charged repeller pushes positive ions through 2 lenses that crudely focus the beam. And then we have a quadrupole ion guide. And that quadrupole ion guide focuses the beam nice and tight. And then it goes into a quadrupole mass filter, mass analyzer. And finally, the sorted ions go into the detector. Let's look at the equivalent for the LCMS. This is not the LCMS you guys are using in forensic tox, but it's a close cousin. We looked at it last time, and I said, look at that hole. That's the inlet to the mass analyzer. So this inlet is at atmosphere. It's at 760 torr. And so there has to be a lot of pumping that goes on to get from 760 torr in the front of the instrument to 10 to the minus fifth in the back of the instrument. That's part of it, but remember, we also need to focus those chaotic clouds of ions into a nice tight beam. So we're going to look at the cousin to this instrument, the one that you guys are going to do in LC Tox, and I want you to imagine that I took that whole circular part that's around the inlet and just pulled it out. So there was kind of a big hole in the front there. And we'll look at what it looks like from there. So if you pull this front piece off, you can see that conical piece is called the ion sweep cone, and there's an inlet right there. It's called an ion transfer capillary. It's a thin tube, and the ions travel down that tube, and you can see at the end of the tube there is a lens called the tube lens, and then there is another lens called the an RF lens, and then there is yet another lens. So we've already gotten more complicated than the lens system we had in the quadrupole GCMS system, which was under vacuum because it had an EI source. So we've got the ions come in the very front. The red circle that I showed you previously, that's the red oval that I'm showing you here. That's where the ions fly in through that tube that you're seeing as a line, the ion transfer capillary. And then they go through the skimmer that helps get rid of neutrals. And then they go through a few lenses before they travel further into the instrument. So now I'm going to show you part of the instrument after you've pulled this whole assembly, the ion source interface, out of the instrument, and we're going to look further down the instrument. So this is a second ion trap for the LCMS that I keep around for spare parts. This is a top-down view. Let's pull it apart and look at what is inside it. Now, that front end has already been pulled out, so you see that hole at the front of it. All right, so I pulled out the guts to the mass spectrometer after the ion transfer capillary there and the skimmer and those first few lenses. So what I've laid down on the floor is the heart of the mass spectrometer that has the last ion optics and the detector and the mass analyzer. So if we take a closer look here, the first thing that we're going to encounter is going to be a quadrupole ion guide. It's just got 4 square poles. So we'll sort of scoot on down the ground here and look a little bit down those poles. You see those 4 poles? That's a quadrupole ion guide like we were talking about before. Now, the ions fly through the quadrupole ion guide, and then past the quadrupole ion guide, we have octupole. That's an octupole ion guide that also helps to focus the ions. And then it moves from there into that disc-shaped guide. That is actually an ion trap. That's the mass analyzer. It flies out the end of the mass analyzer sorted, and that hole is the detector. We can trace the whole thing through with the schematic in the manual. So it starts with the ion sweep cone, and that little hole at the tip, that's the hole that had the red circle around it in the beginning. That's the little hole that sucks in whatever's right near the front of that hole. So we shoot the ions at that hole. They'll accelerate into the hole coming from an electrospray source or a dart source because there's a voltage pushing them. They travel through the ion transfer capillary. They hit a lens, the tube lens. Then they hit something called a skimmer that's designed to get rid of neutrals that just happen to get sucked in by the vacuum. Then they hit another lens called the Q00, lens 0. And then they go into that square quadrupole ion guide, and then 2 more lenses, and then an octupole ion guide, another lens, finally the mass analyzer, which is an ion trap, and then finally the detector. The sorted ions hit the detector. Let's talk briefly about detectors. They're worth talking about. Sometimes I trash talk detectors, but they're actually the unsung heroes. They're quite wonderful. We're going to talk about one particular kind of detector, the electron multiplier, and that is the detector that this instrument has, and a lot of mass spectrometers have electron multipliers. So if we pull the top off here and look at the back end, we see that there's part of the detector on the right, the conversion diode, and then that hole that we were looking at, that's the actual electron multiplier. It'll be easier to talk a little bit more about the physics of it if we look at a schematic. So here we can see the ions flying out of the back of the mass analyzer. Remember, detectors do not sort ions. All they do is convert ions to electrical signal. But if the mass analyzer does its job, we still need to detect these ions. Now, we first introduced these ideas of charge and voltage and detecting frequency, current, and voltage when we talked about GC detectors and the FID. I said, let's hold up a minute and let's talk about actual signal, converting our chemistry to actual signal. So it's true that an ion is moving charge, and we could just directly detect the ion current, kind of in theory, but there's not much signal there for a little packet of ions that have the same massive charge flying out the mass analyzer. So we really want to amplify. We want to amplify the signal and make it easier to detect. Electrons are pretty easy to detect. So the first thing that's going to happen is the ions are going to be attracted at very high velocity. There's a lot of voltage on the conversion diode, a lot of negative voltage in the conversion diode. The ions are going to fly into there. And the conversion diode is configured with material and electrical fields such that when the ion impacts the conversion diode, you get a spray of electrons coming off the conversion diode. But we're a little bit greedy. That's still not enough signal for us. We said, okay, we had one ion hit the conversion diode, or a few ions hit the conversion diode, and we got a bunch of electrons off the conversion diode. That's still not enough. Then it's going to fly into the electron multiplier, which does exactly what it says it does. It's a series of plates, and each time these plates have high voltage on them, and when an electron impacts one of these plates, you'll get 2 or 3 electrons off. So if you put these plates in series, you can take a few electrons and convert them into a readable, useful electrical signal. So you put a few electrons in and you get a lot of electrons out. that gives you a lot more signal, improves your signal to noise, makes everything easier to detect. So let's look at an animation here from the Mass Spec Pro to see what that looks like. We've got a positive ion coming in, striking the first plate, converted to electrons, and each time it's striking a plate, each electron strikes a plate, you get multiple more electrons off, and it's massively amplifying the signal to give you a readable signal. Now, if we take a look at the software that runs this instrument, we can also see where there's a bunch of parameters here. We saw there were a lot of lenses and a octopole and a quadrupole. There's a lot of voltage to control, but just like with the GCMS, this guy also has an auto tune, because that's pretty difficult to do that by hand. So you can spray a calibrant mixture into the instrument and then just tell the instrument, I want you to search out all the different voltages for all the different lenses, the octopole, the gates, all these different ion optics, and optimize them so that I get optimal signal. Okay. So on the right there is going to be all the parameters that we're going to be looking at for running the instrument. So if we blow that up, we can see some of the first parameters this guy's actually running. These are mostly have to do with the electrospray source. It's got the voltage on the capillary, which isn't being applied. But you see at the bottom, the tube lens. The tube lens is here because the tube lens is pretty close to the ion source, relatively speaking. And it's the first lens that the ions see. Now, the next set of parameters that we'll look at will be most of the ion optics. So here we have, you can see this is the voltage for the multipole. There's a bunch of lenses in there, gate lens, there's yet another multipole. So again, there's a lot of ion optics because you need a good tight beam, but also because here we are going from atmosphere all the way down to 10 to the minus fifth. The entire thing is under vacuum, but you have to tune these so that you get a good ion beam, but you really let the instrument do that for you automatically in the auto tune. So now that we've gone through resolution, we went through ion optics, looked at the electron multiplier as a detector, let's get into our first actual mass analyzer, the quadrupole mass filter. This instrument's really great for educational purposes. It turns out it has 3 quadrupoles in it. But let's, here we have the last quadrupole, and this quadrupole determines what ultimately hits the detector. Let's go ahead and pull out this quadrupole mass filter, and we'll take a look at it in more detail. All right, so if we look at it on the end, we can see the 4 poles again, and that path down the tube, essentially, that path down the tube. If an ion gets through the tube all the way, then it gets to hit the detector. We can see that we have these 2 poles, and they're in pairs. This pole is connected to this pole, and the other pole is connected to the other pole with that wire. That's going to be important later. We look at it from the top. It does have this, it has the tubes, the poles down inside. It has this shielding around the outside, that metal sheath around the outside. It's not like the naked octopole we saw before. And here's the other side, where it's got a bit of an optic that obscures the tubes, but you can see there's the hole. If an ion passes successfully all the way through that hole in the center, it hits the detector. If not, it does not. So let's make our own crude schematic here. We've got our quadrupole. We're going to put an ion optic and an octopole ion guide up front, and let's put the electron multiplier in the back. So this is our own very crude schematic. The ions are going to come out of the ion source through the ion optic. Now it's the job of the quadrupole, it's the job of the mass analyzer to determine who gets through to hit the detector. So the mass analyzer, the quadrupole, has to give us the x-axis. It has to spread out the ions so that the detector, they hit the detector one at a time in an organized way, and we're able to discern what mass to charge actually hit the detector. So remember, the detector cannot tell what ion hit it. That's the job of the quadrupole mass filter. Let's get more into how this guy works. All right, so we have 4 poles here, and we're actually going to think of them as 2 pairs of poles, 2 pairs of poles. So let's start with this first pair. These 2 guys are paired up. You can see they're connected by the wire, so we have the red pair here. And we're going to apply electrical fields to these. Let's take a closer look at the fields that we're going to apply. So a quick throwback to what we looked at with FID detectors. We can apply voltage to different plates, positive and a negative. We're going to get the positives attracted to the negative, negatives attracted to the positive. In this case, we're pushing around positive ions for the most part. We're definitely not pushing around electrons. Instead of plates now, we're talking about poles, but we're going to apply a positive voltage to the poles such that with this pair of poles, one of them is going to be the positive and one of them is now going to be the negative. The voltage difference for a quadrupole mass filter is typically going to be 10 to 1,000 volts, but let's suppose that we are putting 500 volts between this pair of rods here. When we've been talking about voltage, we've really been talking about what's called DC voltage, or direct current. And what that means is, if we're applying 500 volts DC, then we turn on the 500 volts, one of the poles is at 0 and the other one's at 500 volts, and it stays at 500 volts. If we turn on the power supply and we turn it up to 500 volts and we leave it for a while, it stays at 500 volts the whole time. So if we plot voltage over time, like we've done above, here we've plotted out 10 microseconds, a kind of short burst of time, but that's a decent amount of time in mass spectrometry, we can see that it's boring. It just says there's a red line. We're applying 500 volts at 0 microseconds, 500 volts at 1 microseconds. We're just applying 500, positive 500 volts the entire time. So we are going to apply this DC voltage, the kind of voltage we've talked about so far in this class, to this pair of poles, but we are also going to apply AC voltage. AC stands for alternating current, but basically what that means is this voltage, as you can see in the plot, is going to change with time. So this voltage is at 0 microseconds, and at about a quarter of a microsecond, it's up to 2,000 volts. And then by the time you get to 3/4 of a microsecond, or 0.75, it's all the way down at minus 2,000, and then at 1, it's all the way back at 0. So the voltage is going to oscillate. The voltage is going to change with time. And the whole trick here is we're going to carefully pick what DC and AC voltages to apply to the quadrupole. And in doing so, we're going to be in control of which ions make it through the tube, which ions fly all the way through, and which ions do not fly through, which ions don't make it through the tube in the center of the quadrupole. Okay, so we're applying this AC voltage. So a good question would be, what do we call this? It's not 0 volts, it's not 500 volts, it's constantly changing. So one way that we're going to express how big this voltage is, because we can certainly make that, we call it the amplitude, bigger or smaller. This particular voltage, this is an example, we're going to call it 4,000 volts AC peak to peak. It's 4,000 volts peak to peak. And what we mean by that is, look at the first peak. It's all the way up at 2,000. Look at the next peak. It's down at negative 2,000. So from peak to peak, you are going from negative 2,000 to 2,000. So you are going 4,000 volts peak to peak. So that's how we're telling you how big this voltage is. This voltage is 4,000 volts AC peak to peak. There's another characteristic to this voltage signal that we need to characterize, and that is how often it oscillates up and down. How many times does it go up and down per second is usually what we say, because we could have, there's AC voltage, a very common AC voltage would be 60 waves per second. That means it goes up and down and back up again 60 times per second. Okay. Now if we look at this guy, we have 10 microseconds here. We have 10 microseconds on the X scale. Every 1 microsecond, so every 1/1,000,000th, every 10 times 1 times 10 to the minus 6th of a second, it's making 1 wave. So it takes 1/1,000,000th of a second to make 1 wave. So what that means is, if we were to sit there and count how many waves, how many times it went up and down, up and down, up and down for 1 second, we would count 1,000,000 times. So this thing goes up and down 1,000,000 times per second. There are 1,000,000 peaks per second. Now, when we're talking about things oscillating or move up and down, the unit for per second is hertz, Hz. So instead of saying 1,000,000 times per second, we can say 1,000,000 hertz or 1 megahertz. 1 megahertz. So we said this signal is 4,000 volts. 4,000 volts peak to peak. We're also saying that it is 1,000,000 peaks per second. That's how quickly these peaks are occurring. 1,000,000 peaks per second or 1 megahertz. So this voltage is 4,000 volts at 1 megahertz. Now, we're going to have to introduce yet another bit of unfortunate historical vocabulary. Unfortunate, in my opinion. We should call this AC voltage. AC means alternating, as in alternating positive, negative, positive, negative. Yes, it's called AC voltage. Unfortunately, it falls into a frequency region called the radio frequency, or RF. So instead of calling this 4,000 volts AC voltage at 1 megahertz, most people are going to say, oh, this is 4,000 volts RF, 1 megahertz, because 1 megahertz is in the radio frequency region. Don't worry too much about that. That's not science. That is semantics. It is AC voltage that's going up and down from peak to peak at 4,000 volts, and it's going up and down 1,000,000 times per second or 1 megahertz. So we have 4,000 volts RF, 1 megahertz. That's the RF or AC voltage we're going to apply to these electrodes. So we're going to apply 500 volts DC and 4,000 volts RF at 1 megahertz. So if we look at the plot of the voltage that we're actually putting on these two rods, it's the combination of these two. It's the sum of these two. So we call it a DC offset. It's 4,000 volts RF at 1 megahertz offset by 500 volts, as you can see in the plot above. Okay, so you're probably saying this is a lot of effort, this is a lot of work. It turns out, though, quadrupoles are really they can be hard to understand. They're very hard to understand, but this is really easy relative to other mass analyzers to build and maintain, and it's cheap and simple in terms of the engineering and the science. Understanding it is not. But it is important that you have some understanding of it. It's a really common question in job interviews or when they're discussing internships or anything where you're going to be running a GCMS. It's really common for them to say, hey, give me a quick description of the quadrupole, or how does the GCMS work? And you describe it to them, and they're like, yeah, tell me about the quadrupole. So you need to have a basic understanding of how this thing works. To be honest, most professors shy away from explaining the quadrupole, even though it's by far the most used mass analyzer. It is the most common mass analyzer in the world by far, but it's the hardest one to explain. So we will a lot of times start with something like the magnetic sector, which is really easy to explain, but it's quite rare. It's extremely rare relative to the quadrupole. Okay, so why are we doing this? Why are we learning all about this RF and DC voltage that we're applying to this pair of poles? Well, remember, the end goal is we're going to make complex electrical fields that are going to give us control over which ions pass through that tube and hit the detector, and which ions do not pass through and disappear. We don't want to forget those other poles, and it turns out they are a pair too. They are paired up electrically. And they're going to have equal and opposite. Everything, the voltages that are applied to them are going to be equal and opposite to what was applied to their companion red poles. So to start with, instead of applying, in our example, when we're applying plus 500 volts DC to the red poles, well, instead we're going to apply minus 500 volts to the blue pair of poles. We're also going to apply an RF voltage. It's going to be 4,000 volts RF peak to peak, and it's going to be at the same frequency, 1 megahertz. So we have this in concert with the minus 500 volts DC, and again we get the summed waveform, which is the 4,000 volts RF with the minus 500 volts DC offset. Now it's easy to see how the minus 500 volts is equal and opposite to the plus 500 volts being applied to the red rods, but to see how the RF voltage being applied is equal and opposite to the RF voltage being applied to the red rods, let's stack up the waveform for the blue rods with the waveform for the red rods. So when we have them stacked like this, you can see they are in fact equal and opposite. The 4000 volts RF with the plus 500 volts DC on the red rods, the waveform on the red rods, is opposite to the waveform on the blue rods. Look, if we look at 0.25 microseconds there, that first peak up on the red waveform, when the red waveform is at its peak voltage at 2500 volts, the blue waveform has gone down and is at its peak bottom voltage at minus 2500 volts. Okay, and then the red waveform goes on from there at about 0.75 microseconds. It's at its bottom voltage, minus 1500 volts. But the blue waveform, at about 0.75 microseconds at that same point in time, is at its top voltage, positive 1500 volts. So we really have created a condition where we have two pairs of electrodes, a blue pair and a red pair, and they are equal and opposite to each other. And we're applying DC voltage and RF voltage to each simultaneously, equal and opposite. Again, the reason we're doing this is so we can control which ions get through that tube and which do not. So this complex set of waveforms that we're putting on these poles generate what's called a quadrupolar field inside the mass analyzer, inside the tube. And whether or not an ion makes it all the way through the tube and hits the detector and is detected depends on its behavior in the quadrupole field. Or one thing that we say is its stability. If it's stable in the quadrupole field, then it survives and passes all the way through the tube and hits the detector and is detected. If it is unstable in the quadrupole field, then it flies out. It flies out of the mass analyzer and is not detected. Okay? Now, these quadrupolar fields are solved by a relatively complex set of equations called the Matthew equations. We are not going to solve these equations, but we are going to look at some plots for solutions of these Matthew equations. Now, because they're telling us whether an ion is stable or not, we call it a stability diagram. And remember, if an ion is stable in a quadrupolar field, then it can fly through the quadrupole and hit the detector. If it is unstable, then it flies out and is not detected. Here we have one of those stability diagrams I was referring to. I did not calculate this. This was calculated by the good folks at Xtrel. Now, this is for mass to charge 219. This is a stability plot for mass to charge 219. This also supposes that you have a 9.5 millimeter diameter quadrupole. That's the spacing between the poles. That's pretty common spacing. And a 1.2 megahertz RF frequency. We are not going to change the frequency during this experiment. It's difficult to make a good stable RF frequency, so for all these instruments, the frequency is going to be pretty much around a megahertz. For their quadrupole here, it's 1.2 megahertz. We're going to leave the physical spacing of the quadrupole constant. We're not going to move quadrupoles around, so the spacing here is 9.5 millimeters between the poles. And the frequency at 1.2 megahertz is going to remain constant. So the instrument that's going to be constant. Now what we can change pretty easily is the DC and RF voltage that we apply to the pairs of poles. So you can see in this plot, they've got DC voltage, positive and negative on the y-axis, and RF voltage, peak to peak, on the x-axis. Again, we're going to leave the frequency constant at 1.2 megahertz. So they have this kind of funny shape up top, and see the mirror on the bottom. Remember, the poles are equal and opposite. So you'll notice that the shape is symmetric about the x-axis. Okay? So if you were in the shaded blue area, so this is mass to charge 219, if you are applying RF or DC that is inside the shaded blue area, then mass to charge 219 is stable and will successfully fly through the quadrupole and hit the detector. If you are outside of the blue shaded areas, then mass to charge 219 is unstable and will not make it through the quadrupole. So let's suppose here that we apply about 350 volts RF voltage peak to peak to the red pole, and then about 35 volts DC to the red pole. That's that red dot that you see in the diagram above. Now we're going to apply equal and opposite voltage to the blue pair of poles. So we'll apply 300 volts RF, but it's 180 degrees out of phase. It's that opposite up and down business on the blue. And then we'll apply the minus 35 volts DC to the blue pole. And when we do this, mass to charge 219 will remain stable in the quadrupole and will traverse the entire quadrupole and impact the detector and be detected. Let's change the settings on our quadrupole. Again, we're going to leave the settings for frequency the same, but let's switch the voltages. So now we are applying, what is it, around 525 volts RF and about 60 volts DC, and equal and opposite to the blue poles. We are now outside the shaded blue stable region. So now mass to charge 219 in this quadrupole under these settings is unstable. So at these voltage settings for the DC and the RF, mass to charge 219 is unstable in the quadrupole and will be ejected from the quadrupole. It won't make it all the way through and will not be detected at the detector. Let's look some more at these stability diagrams. The first thing is, since everything's equal and opposite, we can just look at the top half because it's going to be the same. So let's just look at the top half. So we said if we apply this voltage here, the ion is going to make it all the way through and hit the detector. We can go down here. We can drop the DC voltage down to like 20 volts, and we're at 425 RF, still stable. We can shift over here and be at 275 volts RF, 25 or so volts. Okay, but if we shift outside of the stable region, then mass to charge 219 will not make it through the quadrupole and will not be detected. So inside, whatever RF and DC voltages are inside there will not be detected, or you will be detected. But if you pick an RF DC voltage that is outside the stability region in the stability diagram, then you'll be ejected from the quadrupole and will not be detected. But we don't want to just detect one ion. It's really common for us to scan between 50 and 500, and we want to be able to detect mass 50, 51, 52, 53. So each mass to charge has its own stability diagram. And here you can see 3 different ions and their stability diagrams plotted, courtesy of Xtrel. You can see mass to charge 28, mass to charge 69, and mass to charge 219. Now, if we start applying our RF and DC voltages, if we apply this about 50 volts RF, 8 or so volts DC, mass to charge 28 is stable and is going to pass through the mass analyzer. Mass to charge 69 is not. That red dot is just outside the stability region for 69, so 69 will be ejected and won't make it through. 219, that red dot is outside the stability for it. It will also be ejected. We can switch our DC RF voltage. We can ramp up the DC and the RF up to, that looks like about 18 volts DC, 125 volts RF. Now we're going to detect mass to charge 69, but we're outside the stability region for 28 and 219, so only 69 will survive and hit the detector. Then we can ramp up our voltages even more. We can go up to about 425 volts RF, and that looks to me about 50 volts DC, and then only of those 3 masses, only 219 will make it through. So this is how we can use the quadrupole to sort the masses for us. We're going to scan the DC and the RF voltages so that we only let one mass through at a time. So we'll start at whatever the lowest mass is we want to detect, and then we will ramp the DC and the RF voltage simultaneously. And as we ramp these, only one ion at a time will be stable. One ion will survive, and the rest will be ejected. So as we move up the ramp, if we started at, say, mass to charge 20, well, in the first instant, only mass 20 was detected, then only mass 21, then only mass 22, then 23, and we go all the way up to the upper mass we want. So we scan through the mass range, and we tell the detector, okay, based on my RF-DC voltages, when I first start, at the time I first start, mass to charge 28 is coming through. And then I'm going to shift, and then the next instant 29 is coming through, and the next instant 30. And the detector knows, well, the computer knows when which mass to charges were supposed to hit the detector. So then it takes the signal from the detector as a function of time, and it knows what the RF and DC were, and it takes that information and constructs the mass spectrum based on that information. All right, so let's take another look at this, courtesy of this clever guy at Waters telling us about his quadrupole. So here's a stability diagram with RF and DC values, 4 different masses, and we're going to apply a ramp, a DC RF ramp to this. And as we do, over time, the masses that correspond to it were detected. Now, you can look at that ramp and see that we're almost hitting the tip of each stability region for each mass, but not quite. And that gives us a little bit broader peaks. If we increase the slope of the ramp there, so we're just barely touching the tip of each mass region, then it skinnies up the peaks and we get better resolution. But we don't really care with the mass analyzer. And we're going to set the mass to charge, we're going to set the slope, that is, of the DC RF ramp such that the resolution is set to what's called unit mass. So that means integer mass. So we're going to set the ramp such that, okay, now mass to charge 20 is coming through, now 21, now 22. We are not going to try and use the quadrupole to discriminate 20.1 from 20.2 from 20.3. We're just going to do unit mass with it and keep kind of a relatively gentle slope and relatively broad peaks. In GCMS, if it's working right, we don't need resolution. We don't need resolution because our information is coming from the fragmentation pattern. Now, we have to be really careful and make sure that we have pure compound coming through because our resolution isn't good enough to distinguish between peaks that are close together. And when you have a bunch of fragments, a big messy spectrum, if you have a mixture, you're going to get peaks pushed together. So we have to be careful to make sure this stuff is pure when it goes into the mass spectrometer, but that's not a problem in a GCMS because the GC purifies it for us. Okay, good job hanging in there for a bunch of physics and voltages and things. I promise it is important that you have some understanding of the quadrupole. It is by far the most common mass analyzer in the world, and it's very common for you to be asked about this when people are assessing your instrumental skills in an interview. Now that we are masters of the quadrupole, let's revisit the quadrupole as an ion guide, as an ion optic. So we saw that guy used as an ion optic. The trick there is you turn off the DC. You turn off the DC and go into RF only mode. And in that mode, it's going to pass multiple ions. So for the ion guide, you want it to pass pretty much all the ions. So you don't want it to discriminate. You're not trying to filter. So you're going to set the same thing with the octopole, set it to low voltage RF and turn off the DC. And then you're going to pass all the ions. But as they pass through the ion guide, like you saw in the previous animations, those beams are going to get nice and focused. Okay, good job hanging in there with discussion of resolution and the complicated discussion of the quadrupole mass filter. Let's finish up with a discussion of the ion trap, which everything we just talked about with the quadrupole mass filter is going to come back into play. So let's look at what we were just looking at, where we said, okay, we've got an octopole. We're going to apply low voltage RF. We got this quadrupole. Let's isolate our quadrupole. And you know what? Let's put in another quadrupole. Let's make a circle of identical quadrupoles. Okay? Now we know that we can pick our RF and DC voltages to make certain ions stable or unstable. Let's go with our friend 219 here. We'll pick a voltage where 219 is stable. And this is a really cool trick, because if we set all the quadrupoles to RF and DC voltages such that 219 is stable, this guy will race around and around, and we've trapped it. We've trapped 219. But if we switch our RF and DC voltage so that it's not stable, it will fly out. And this is the basis of the ion trap. Now that mass analyzer on our LCMS is an ion trap. So let's take it apart again. And let's look physically how we're going to make this ion trap situation happen. So we paid attention to the ion optics before. We even looked at the detector. Now let's look at the actual ion trap. That is the actual ion trap. It's called a quadrupole ion trap. And if we look at this cool cutaway by Neil Kelleher's lab, you can see that when we pull this guy apart, it has two identical opposite pieces called end caps, and in the center there's this ring holding them together. It turns out this geometry is essentially the same as that circle of quadrupoles we made before. This is an ion trap from a Varian GCMS instrument. It's a nice simple ion trap, so it's kind of fun to take apart and show you guys. You can see that hole right there. You can actually put the GC column in there and spray neutrals directly in the trap. Now on this end cap, we have those perforated holes for ions to pass through. In truth, in this case, it's for electrons from the EI source, but most of the time it's for ions. On the other side, the other end cap has that pinhole. That's where ions are going to be ejected from the ion trap and hit the detector. So let's take it apart. There is the first end cap where the ions would enter in, and you can see it's got that rounded shape. So the ions essentially see it as a quadrupole. And we just have empty space in the middle because we want to keep the ions trapped in the middle of this trap. We don't need them running around a racetrack. We're going to keep them trapped in the middle. So this ring electrode is just going to facilitate the end caps, holding them in the middle. And then there's that pinhole in the other end cap. This is different than the quadrupole, where in the quadrupole, if you were thrown out, you were not detected. You had to make it through to be detected. In the ion trap, it traps everybody. And the way that you get detected is you get thrown out of that ring electrode with the pinhole, and the detector is right there. So if you get thrown out of the ion trap, then you get detected. Okay, so this is a really cool video this gentleman made where he's going to use two spoons as end caps, and he's got his ring electrode there. It's just a piece of wire. He's going to take some flour instead of doing, small tiny ions. He's going to take some flour. He's going to turn off the lights and use this green laser so that you can see the trapped particles. So the flour is going to get charged. Going to put a little bit of that in the toothpick and just try and get some of the charged stuff in there. And look at that. Okay. You guys see that? You see the light? Those particles are moving up and down. They're trapped. Those flour particles are trapped in that electrical field by the quadrupole electrical field. Instead of kind of racing around in circles, they are moving pretty quickly there, but they're trapped in an oscillating motion in the field. Now, if he turns up the voltage, which he's about to do in a second, if he turns up the voltage, then it will throw them out. It will eject them from the trap. So in just a second, he's going to crank up the voltage, and they are going to fly out. There we go. They were thrown out of the trap. So if we go back to our friend, the stability diagram, what we're going to do with the ion trap is set RF only. So now everybody is stable in the trap. Everybody's in the middle. Everybody's nice and stable in the middle of the trap. But we're going to gradually increase the RF voltage. And as we do this, the ions will be thrown out of the trap sequentially. So you can see if we go along the x-axis a little bit, if we increase the RF voltage, right now 28, 69, and 219 are stable. But as we increase, 28 is not stable, now 69 is not stable. So 28 flew out and got detected, and then 69 flew out and got detected. And then when we get all the way to the end here, 219 is thrown out and gets detected. So in the ion trap, we're going to make everybody stable and everybody happy and sitting on the inside. We are going to trap the ions. And then we're going to ramp the RF voltage to sequentially eject the ions from the trap and detect them. Let's look at this cool animation for one of our ion trap instruments. Ions fly through the source, through the ion optics. They arrive in the trap, and they've got a lot of energy. We got to cool them. We don't want them to get too excited and crash into the walls. There's another animation for this I like better. Here we go. You can see a little bit clearer. Now you have to use, there's actually a pressure of about 10 to the minus 3 torr of helium that we say cools the ions, like to calm them down there. It made sure the ions didn't get ejected from the trap. If they come in and they have too much energy, they're going to smack the walls and be neutralized, and we don't want them. We want them all to survive and be stable in the center of the trap. So as they come flying in with all this energy, They gently smack into the helium, and that cools them down. That takes away some of their energy and calms them down, and they sit there in the middle of the trap so that we can scan them efficiently. If you do not use this buffer gas, then the consequences are severe. The quality of your spectra decrease significantly. So once we've got them trapped, we're going to scan the RF voltage. You can see a stability diagram on the side. And as we do, oh, that guy became unstable. It pops out and gets detected. Next biggest mass, next biggest mass, next biggest mass. So as we scan the RF, where they're sequentially detected, starting with the smaller ions are less stable at the lower RFs, and the larger ions stay stable until the biggest RF values. And that gives us this mass spectrum. So we trap the ions and we sequentially scan them out to detect them and give us our signal. So the ion trap has a big advantage called MSMS. We'll talk about that in the next video. But the main reason ion traps are used in forensics is because they can tolerate higher pressures, so they can be made portable. So this is a mobile gas GCMS that's made by a company called Griffin, Fleer Griffin, and it is quite actively in use by the military, and you can see they've got this cool animation here, but they actually do have these guys deployed. They've had deployed these to Iraq and Afghanistan, and they sell them simple units. You can see that's basically a headspace unit. They can capture vapors and then come over and put it on the top of the GC column and heat it so the vapors come off. Here is a drug unit that is doing vapor testing at the crime scene. But they can sometimes even get drug vapors off of there. And here's a mobile lab system. And you can see that on the left, you can just do a traditional injection also. They even actually make an auto sampler for this instrument. And with all these technologies, when you're going to make it deployable and give it to non-scientists, you need to have nice, simple software like this. You can see she can just click through and say, oh, it's not liquid. It came from this unit. And then say which, tube it came from. And then it runs. And she doesn't need to see, as a graphic while it's running, she doesn't need to see the chromatogram or the mass spectrum. It's just going to say red light. There was toluene in there. Now, you can go through confirmation equals action. That means she's going to call somebody up for verification. But you can go through and pull the gas chromatograph and the mass spectra from the data for someone else to review. Another model of a fieldable ion trap is called the 908 devices. This is an array of tiny ion traps. It's real small, so it pumps down real fast. And you can see he holds a sample right there, and it alerts. It's styrene. That gives you its identity. What they're bragging about here is it doesn't get messed up by background interferences. So this guy has been deployed in forensics in Massachusetts. This is from Detective Lieutenant Patrick Glynn, nice guy who gave me the pictures of this guy being used. So both of the units have been deployed. Now, they're expensive. They're not going to be as widely deployed as handheld spectroscopic instruments, which are cheaper. But there are agencies and some officers accessing these fieldable devices. A really significant instance of this is the Netherlands Forensics Institute, essentially the Netherlands equivalent of the FBI crime lab. They have this system called NFIDent that is really cool, where you can see, number one, the police find the evidence, the drug evidence, and then they fill it out, and essentially then a lab tech runs it on that Griffin instrument, and they get red light, green light. But then they can sort of Skype in with an actual chemist, and when they get the red light, like she called on the phone, and then the chemist can pull the data off the instrument, look at the footage of the person injecting to make sure it was proper, and then look at the chromatogram and the mass spectrum. And if it's good, and the data is good, then they can dispose of the evidence right there. I shouldn't say dispose, but it's done right there. It doesn't need to come back to the crime lab. They can take that information to court, and the evidence is set at it as is. It's quite an efficient system. Again, that's the big advantage of ion traps at the moment. There's also MSMS, which we'll talk about in the next thing. But in forensics, the big appeal of ion traps right now is that they can tolerate higher pressures, so you don't need giant pumps, and you can build smaller instruments that you can potentially send out into the field because they can tolerate those higher pressures that other mass analyzers cannot tolerate. All right, so we went through resolution and how that's the main criteria for sorting mass analyzers. Then we went through ion optics and how those are important to make sure you get your ions into the mass analyzer. And of course, we went over one particular detector, the electron multiplier. And then we went over the most complicated to explain, but in practice, the simplest mass analyzers, which would be the quadrupole mass filter and the ion trap. In the next video, we're going to finish up with discussion of time of flight, the Orbitrap, which are both very high resolution mass analyzers, and then we're going to go into MSMS, which is getting fragmentation in the mass analyzer, and we'll talk about the instruments you can use to do that, one of which is the ion trap.